I'm going to talk a little bit about what HPC on AWS looks like and how that's a little bit different than sort of a traditional HPC center, and the role that Spack plays in getting software to our customers, and how the build cache helps improve that experience, and recent improvements to Spack to really maximize the use of the build cache. So I think we all know this. This audience is very familiar. We can't just apt install some package. We really want to squeeze all of the performance out of our hardware. We have, large 2-socket systems with many cores, and AWS really sees Spack as a way to help deliver that performance to our customers without a lot of very detailed steps that we have to provide them. So consider the comparison between a traditional HPC center, and even this, is probably maybe even predates the ECP sort of thing, where you have an image of an idea of sort of one system that you're looking at that just has a few configurations. The system administrators are probably very familiar with the compute nodes, what software libraries they want. There's obviously challenges in keeping those libraries up to date, but they have sort of a direct line to the users through shared file systems, and users essentially log into the system, module load the software they're interested in, and then maybe they build some things on top, or they just get everything from modules. On AWS, we do not have a direct line to our users. We are not on their systems. We provide the provisioning for compute and the network, and it's up to them to configure the system. And at the same time, we want them to have the expectation of good performance, and that comes with having software that's tuned for the system. Problem comes too when there are so many different configurations that the user might choose. So we have a variety of GPU families, a variety of CPU families, including AWS's Graviton, as well as Intel and AMD. The customer might choose a particular compiler based on preference or need, and they have the flexibility to change their operating system. And all of these together make a combinatorial explosion of different ways that they can choose to configure the system, and there are lots, depending on the application they want to run or the region they want to run in, there's a lot of good configurations here. This is not just an explosion of bad problem space. There's a lot of good flexibility for customers that they should try to engage with. Spack provides a good way for us to give those customers the guardrails to say, if you use these Spack project stacks with YAML files that sort of give some preferences, make sure you use this version of libfabric for this MPI, you can reasonably expect that the user is going to follow the path and get to a optimized software build for their configuration. So this is how we recommend the customers engage with Spack. We provide them instructions to install Spack, both the basic Spack, but also pointing them at a binary cache for their stacks, for a stack. And then AWS works with Spack community to make sure that the stacks that we're recommending are performant and available for what they need. These stacks provide opinioned defaults. I mentioned that a little bit, but they also include the optimizations that are relevant to the microarchitecture that they've chosen. And that's really important, because if they just grab a basic binary that's pre-built, we would have to supply so many different microarchitecture configurations that it would get out of hand for us very quickly. Not only does this help a customer that is starting a new cluster, but it also helps customers be flexible in how they use their clusters. They may need to follow capacity by moving from region to region. They can start their cluster on Monday morning and do a Spack install and expect to be using their compute resources with their application in 20 minutes or so, instead of starting from scratch, typing, setup, whatever, and then having to wait hours for compiles or manually fiddle with a bunch of things until it gets working. So the ability to rapidly iterate on starting from scratch and going to a working application gives them a lot of flexibility so that they can move regions, they can treat their clusters as ephemeral and only pay for them when they need them. So the way that we do this is we have an installation script. It works for parallel computing service as well as parallel cluster, supports a variety of operating systems, and provides the tuned configurations for Intel, AMD, and Graviton through packages.yaml. And the model that we take is try to install it once per cluster and install it onto a shared file system whenever possible. And this is already used by the community, and it's available in the Spack configs repository beneath Spack. We have some samples here that the AWS samples that we use, but we've also seen community adoption as well. To get started, it's basically curl the install script from the repo and run it. And it's designed to be a hands-off installation. I think we've seen sort of a similar story on a few different talks this week about how do we get started. We chose this script installation method because we're going to do things like choose which path we want to install to. We want it on the shared file system that the user can configure to be /shared or /fsx or whatever. It also chooses which packages.yaml file based on the microarchitecture that it's going to download and sort of put into the user configuration. And it also adds a build cache into the path. So these are all things that normally, if us as developers are sitting down, we would do a git clone, but then there's the few extra steps after that, and this helps automate those few extra steps. I think we've talked a little bit about sort of inside discussions. Maybe there should be a plug-in way or some other common way. I think we're all kind of doing the same kind of approach here. So the rest of my talk, I want to talk a little bit about the binary cache, the build cache. So collaboration between AWS, E4S, Kitware, and the National Labs, Lawrence Livermore. We host the build cache on S3, and it provides substantial, like 20x speed up for common Spack packages. And this is useful not just for users on cloud service providers, but also on-prem and even just on your laptop. The goal from a quick stand-up of Spack is to maximize the use of that build cache so that the experience is not download Spack and then spend the next 3 hours compiling things, but rather download Spack and poof, you have the application that you want. It also makes the extensive Spack CI coverage possible by reusing pre-built packages. So as an example, when a user gets started, this is what a GCC installation looks like. As each one of the packages goes by, it is first downloading the package from Amazon CloudFront. Each of the signature files is being validated with GPG. Spack is then unpacking and fiddling with a few paths to relocate the binary to the install path. And this is the last step here, GCC extract and installed. So it takes about 25 seconds to install GCC, assuming you have a build cache hit instead of a hash somewhere that's changed that makes you start from scratch with some compile. In order to understand, as developers, to understand how the build cache is populated and how we get users to install Spack, we also provide all of the configurations in the Spack repositories. So Spack configs I already talked about for post-install, which is the sort of getting the first step to installing Spack. The GitLab runners creates the containers that the CI uses during testing, during CI testing, and it also is the containers that the binary cache is populated from, and then the recipe for actually making the matrix and building the configurations for each to populate the build cache is contained in the Spack core repo under the GitLab Cloud Pipelines stacks configuration. So by inspecting this, users sort of understand exactly where the configuration comes from, and this is how we modify things if we want to add another application. We go to one of these places. In picture form, this is kind of what it looks like. Users make a pull request that goes to GitLab, where runners are set off, and some of them on EC2, some of them on HPC centers. Those runners produce binary packages that get uploaded to S3, served back via CloudFront, and then are ready for users to ingest. And so it stays up to date every, I guess actually in a scheduled daily or so run. Okay, so in order to maximize build cache hits, I think there's two things that I want to emphasize have improved that experience recently. John Guar talked about the splicing. He gave an excellent overview of splicing. I think this is really important when you want to reuse that build cache. The issue of making a small change to a library for possibly a bug fix or maybe a minor version upgrade to get a new feature that is needed. Splicing can let us swap, say, HDF5 out from underneath a large project and not have to rebuild everything on top of it. And of course, we already talked a little bit about making sure the ABI compatibility is there or use automatic splicing. This is also, I think, useful when we have lower level, when we talk about moving from one operating system to another, not having to have a stack for every single operating system. We can take things that are slightly different and allow splicing to account for slightly different versions that don't matter from an ABI point of view. The other recent improvement is compilers as nodes. We had another great talk about this earlier this week. The reason it helps the binary cache is it really accurately separates the compiler dependency as a runtime or a link time difference. And critically, it means that you can pull packages from the binary cache even without the compiler. You don't necessarily need to have the compiler in your tree for every package that you download from the cache. There are some, so this is a recent improvement. It really needs developed since March 25th. And there are some, we talked a little bit about it on Tuesday, I think, about there are some breaking changes, so you can't just jump back and forth between those two versions when you're testing. The next steps, use it, contribute, try the develop branch. We're aiming for sort of maximum reuse of the binary cache. Ideally, I'd like to see Ubuntu, Red Hat, Amazon Linux 2023 all have an experience that doesn't build hardly anything from source by default. And then on top of that, user installs the specific application they want, and whether that builds from source or not, I'm not so concerned about, but having the sort of basic installation ready and waiting is the experience that we're looking for. So find us on Slack or email me, GitHub, whatever. That's it. Questions?
Okay, any questions? Yes.
Thanks. So, the deployment model that you showed earlier about on-prem HPC versus, cloud,
yes.
really early on. A lot of university clusters are, looking looking more like, what you might want on this model because a couple of reasons. One is that our clusters are really heterogeneous. Our funding is piecemeal. We have rolling purchases, lots of microarchitectures. And another thing is that, like, what we hear a lot from users is that our central software stack is just failing them. It's failing to satisfy them. Some sites, like, NSF Open Science Grid is always bring your own software. A lot of university sites are just moving completely to bring your own software. So, like, do you think, like, it's do you see pros and cons to using, literally this or similar model with Spack build caches to have, like an on-prem site do completely bring your own software?
Yeah, I think one of the things that I've learned more from, obviously Spack came out of an effort to take what was traditionally, what was traditional view of HPC and realizing that's no longer true, is for the reasons that you said. And so Spack is being used for those reasons, and it's the same reasons that we like to use them. So as far as, I guess the question is, are there downsides to going to this? I guess, no, I think it's definitely the right way to provide a lot of different configurations to the user without having to maintain by hand all those things. That's what the CI and runners and all those are for. So,
Thank you.
That.
Thanks. One more follow-up on that question. I want to point out that, like, for the Spack binary cache, we found for users on AWS that they can get up to 11x speed up on their applications, right? And that's because they don't know the tuning tricks that we do that we can provide through the Spack configs. So there is value to using a centralized config, maybe not a central distribution of applications, but to give them the guardrails, right? And then my question is there anybody in the room who's using the binary cache that's had a lot of misses? Because what I'm curious about is, how do we get from those misses to the intelligence to go build the right package configuration to put it in the binary cache as an automation? Right? Right.
It looks like Todd is very eager to answer your question.
So Ryan talked a little bit about this in his talk. The binary cache, when we first started it, was based on just the most common operating systems that we test on, right? And Spack historically has not had, it was very strict about OS compatibility, right? It would say, like, okay, you built on Ubuntu 18, sorry, you got to deploy on Ubuntu 18, or I'm not going to use that build cache. We changed that, and we have the OS compatibility, at least on Linux, is now done based on libc version, right? We're just kind of assuming that, if you do externals, then you know what you're doing. And if you're using Spack, then the only really thing that you rely on from the system, especially now that we have the runtime libraries, is libc. So Ryan talked about this, but we're going to restructure the public build caches so that essentially they build on each other, and that there's like a portable base, so that there's very likely to be a hit at the lower levels, and then fan out the optimized stacks on top of that. And I think even those might be more generic than what we do right now, right? Like, so they could be like, we could have an x86 64 v3, a v4 one, and different optimized architectures for different types of things. But I think the goal is to have fewer binaries and broader applicability. But still maintain optimizations. So we're moving towards that.
And like you said, you don't have to micro-architecture optimize your compiler.
No,
or everywhere.
Or CMake.
Or CMake,
yeah,
right. Exactly.
Well, I don't know. Bill might like us to micro-optimize CMake, but there's I'm not sure. Yeah, so that's where we're moving towards, and the views that Ryan talked about yesterday will make it possible to do that without duplicating all your binaries all over the place, which I think is key. It took content addressable build caches, which is what we just merged earlier in the week, and that's a big deal. Like, I think we kind of undersold it in the talk, but we're very excited about that.
Yeah.
All right, let's go ahead and thank our speaker again.